sure. So because I had counted on 15 minutes.
Good.
Okay.
So it's the time.
If not
So
more.
yeah, we will
Okay.
resume the afternoon session, and the first speaker is Amjad Ashuriun. Is it correct?
Yep. Yeah. Yeah. Perfect.
So he will talk about examining the end of inflation from the primordial black holes mass distribution and gravitation waves. So please start.
Thank you very much for giving me the opportunity to talk in PASCOS. As the convener mentioned, the title of my talk is Examining the End of Inflation from the PBH Mass Distribution and Gravitational Waves. And it's a it's a talk based on this paper in collaboration with Dr. Abbas Al-Rostami and Javad Taqizadeh Firuzjaei. LIGO discovery of gravitational waves from mergings of the black hole in the mass range of tens of solar mass rejuvenated the interest in primordial black holes. Of course, the mass of the black holes is bigger than the mass of the sun. So these black holes could be astrophysical, coming from the collapse of the stars. However, as pointed out by the John Hopkins group and Sasaki group in Japan, they may also be primordial, coming, for example, from highly compressed matter radiation over densities. Because the inferred merger rate is compatible with their density, the density of the black holes being less than the dark matter energy density. If the black hole is primordial, its mass could be bigger or smaller than the solar mass. Of course, it has to be bigger than M Planck in order to avoid quantum gravity issues for black holes. So so the mass of the primordial black holes could span a wide range. So there are different mechanisms for production of primordial black holes, as first pointed out by Novikov and Zeltovich in East and Hawking in West. For example, collapse of a large overdensity fluctuation during radiation-dominated phase is one of the mechanisms of production of primordial black holes. In this case, horizon reentry of a mode during radiation-dominated with large fluctuating amplitude due to its gravity over pressure just crumbles and PBH will be produced. The overdensity has to be bigger than a threshold that in a radiation dominated phase so it's bigger than CS squared, where CS is the speed of propagation of fluctuations during radiation dominated phase. The mass of these primordial black holes is roughly proportional to the mass of the horizon by a factor of gamma that Bernard Carr worked out in 1975, and to be of order of 0.2. The mass of the primordial black holes is related to the scale of nonlinearity with large amplitude in this phase. So if you want to just, for example, get a 30 solar mass black hole, then you need an overdensity at the scales of roughly 10 to the power of 5 megaparsec inverse. Inflation is a prime candidate for generation of such fluctuations. However, in the range of a scale that we have probed, about 10-fold, the amplitude of density perturbation is about 10 to the power of -9, and the spectral index is nearly flat. For such an amplitude of density perturbation, the abundance of the primordial black holes would be quite small. So we need to generate large fluctuations at smaller scales. And what would be the mechanism of this enhancement is also something that we worked out in a paper which modified the dispersion relation from Lorentzian dispersion relation to the sextic dispersion relation. And this is a talk that my collaborator Abbas Al presented yesterday. Another mechanism of production of primordial black holes is the collision of bubbles, as pointed out by Hawking, Moss, and Stewart. And the primordial black holes generated through this mechanism is roughly monochromatic and is given by this relation, the mass of the primordial black holes. For example, if QCD phase transition is first order, then the mass of the black holes would be about 10 to the power of minus 3 solar mass. The mechanism of nucleating cosmological defects such as cosmic strings and domain walls during inflation is another mechanism for production of primordial black holes. Especially this one is the one that we will focus on to construct a double field inflationary model in this talk, in order that produces the primordial black holes as bubble walls nucleated during inflation, and will give rise to probably the primordial black hole explanation for dark matter. In this scenario, subcritical bubbles with radius smaller than the critical mass collapse due to their tension, forming primordial black holes in the post-inflationary phase. The ones that are bigger than that the critical lengths that I will point out later will exponentially expand under their gravitational repulsion, and wormholes connecting the surrounding parent FRW universe to the baby universe is formed. And these wormholes will pinch off in a light crossing time scale and leads to production of two black holes at the two mouths of wormholes. So that will be just the primordial black holes we observe. The resulting PBH mass spectrum has a wide distribution of masses. However, the heavier ones are those that are created much earlier in the course of inflation. So there are two open windows, roughly open windows, for generating PBHs from other considerations, such as evaporation of the black holes, femtolensing, and other stuff, CMB, mu distortion. So one is the 10 to 100 solar mass range, in which the black holes can constitute up to 10% of the dark matter. The other one that I will focus on in this talk is 10 to the power of minus 17 to 10 to the power of minus 13 solar mass. And in this mass range, the primordial black holes can constitute up to 100% of the dark matter. So as I said, my aim is to construct an inflationary model that produces this the primordial black holes through the nucleation of bubbles that happen during the course of inflation. In this scenario, I especially focus on a double field which resembles the hybrid inflation, but the end of inflation is something that will just consider to be an open possibility. Rather than second order, it can be first order or even by violation of the slow roll condition. So as inflaton is up on the hill, you will see that the potential in the phi direction will look like this. As phi rolls down further, the potential develops a inflection point, and then gradually the minimum that develops here becomes a true vacuum, and the possibility of phase transition from the false vacuum here to here just enhances. And the end of inflation can happen either a slow roll. So here the mass direction in the psi direction can become tachyonic, and then the rolling would occur. Or it can happen through a first order phase transition. So bubbles will collide with each other and then produces just the end of the phase transition, and nucleation of the bubbles will complete. Or inflation can happen can end by a slow roll violation, and end of inflation can happen either first order phase transition or a slow roll transition. And these are possibilities that we will consider in this talk to just discuss to see the observational signature. So the model is the extended hybrid inflation. So the original one is the one with m squared phi squared. That was just the one worked out by Copeland Liddell. And in this case, so the scale of inflation is quite high, m squared phi squared, in order to be compatible with latest observation. And the produced, scale of produced masses for the primordial black holes would be quite small. It would be from 1 gram to 100 gram. So here I have discussed different possibilities. As I mentioned, one possibility is inflation ending via slow roll in the rolling direction. And then the exit from false vacuum decay to the true one happens either through second order via tachyonic instability, or it can happen through first order phase transition. End of inflation can also happen. End of inflation and just settling to the true vacuum can both happen simultaneously through a first order phase transition. And there is a fourth probability, which is observationally from the aspects that we will discuss here, is indistinguishable from possibility A, in which end of inflation happens through a second order phase transition. So these are the possibilities that we will discuss. As I mentioned, the mass of the primordial black holes for that quadratic model is from 1 gram to 15 gram, which is quite small, and these primordial black holes will evaporate soon after inflation. We want to look for primordial black holes in this range. That would mean that the scale of Hubble parameter should fall in this range. So that would mean that there will be no gravitational signature for the model at the CB scale. So this is one signature of the model. However, because of the first order phase transition that can happen at the end of inflation, there will be gravitational waves from bubble collision that in principle has proper frequencies that falls into the window of sensitivity of the LISA. In principle, it all depends on this parameter beta over hf, where beta is the length scale of time scale of the first order phase transition. In order to lower the scale of inflation, we use the inflection point inflation. So we want also to just satisfy the constraint, the CMB constraints that are given by this. The pure inflection point inflation would not be able to achieve that. I should also mention that in such a scale of inflation, you need only 40 folds of expanding acceleration in order to solve the problems of a standard Big Bang cosmology. So, one thing that one should mention is that the reheating temperature in that scale is quite still high, bigger than MeV. So nucleosynthesis has no problem to occur. So we deviate from inflection point inflation due to the reason that I mentioned. So inflection point inflation produces a spectral index of 0.9, which is too small to be compatible with Planck latest results. So we deviate from inflection point inflation in this way. So then for such a relation between the trilinear term and the mass term, then one can work out the spectral index, the amplitude of density perturbation. From the scale of inflation, from the mass of the primordial black holes, the scale of inflation is roughly fixed. We can set, for example, m and phi naught in terms of each other. Then from the other parameters, we can fix the parameters in the rolling direction roughly. We also assume that the lifting of the false vacuum in the rolling direction is quite small in comparison with this scale of inflation. So V naught is much less than m squared phi squared, which would give rise to an inflationary scale of roughly 10 to the power of minus 24 m Planck. So from these considerations, the CMB considerations, we can approximately fix the parameters in the rolling direction. Now we want to realize the scenarios about the end of inflation the way that I mentioned. So the scenario A is the one in which the rolling field becomes tachyonic after inflation ends by a slow roll violation. This happens by fixing, for example, the parameters of the perpendicular direction of the potential in this way. Also, we have tuned the parameters in during inflation such that the probability of phase transition is quite is of order of 10 to the power of minus 18, and this is required in order to just give rise to just enough number of PBHs. So the other possibility B that I mentioned is that first order phase transition kicks in after the end of inflationary era with the slow roll violation. So inflation ends via slow roll, then first order phase transition happens after that. And possibility C is that the first order phase transition kicks in after the end of inflationary era with the slow roll violation. So this is the possibility C that I mentioned. So as I mentioned before, reheating temperature is still high enough for this scale, for this Hubble parameter in order to to have successful nucleosynthesis. In B and C, due to the first order phase transition at the end of inflation, we can have a stochastic background of gravitational waves. And in possibility B that I mentioned, where first order phase transition happen a bit after the slow roll violation, the peak frequency and the amplitude at peak frequency falls into the LISA sensitivity band, so we would be able to see the signature of the model. In possibility C, where inflation ends via first order phase transition, so settling and inflation ending happens both via first order phase transition. The length of first phase transition is quite small, so that suppresses the amplitude of the resulted gravitational waves, and also moves the peak frequency to 10 to power of 10 hertz, which is quite large. And probably, I mean, the sensitivity can be only reached by tabletop experiments, maybe in future. You can also just work out the mass fraction of PBH. So as I mentioned, you will have subcritical and supercritical ones. And because of the time, I do not have that much to just go through it. For the subcritical ones, you will see that it's roughly constant, but for supercritical ones, it just decays like m to power of minus 1/2. So the subcritical ones, due to there is a lower bound, there is a lower bound for the mass of the primordial black holes that can produce, and that is because of the um, quantum fluctuations that change the shape of the resulted bubbles. So you cannot just make subcritical black holes smaller than mass just MF. And so the form of the mass function for the resulted power, the resulted primordial black hole takes this form. So these are the subcritical ones, and these are the supercritical ones. And you can find out the total mass of a total fraction of primordial black holes contribution to the dark matter. And as I mentioned, here the rate of nucleation of bubbles during inflation enters to the argument, and we have tuned it to be at about 10 to the power of minus 18 in order to get substantial fraction of dark matter. In possibility B, where first order phase transition happen by a time roughly about 10 to the power of minus 6 h minus 1 after the end of a slow roll violation, the time scale of phase transition is hf minus 1. But supercritical ones need a time scale to form and the wormhole to pinch off at time scales of roughly much bigger than hf minus 1, where h is the Hubble parameter of the false vacuum. So these supercritical ones will not have the time to form because of the fact that the phase transition will complete in time scale much less than hf minus 1. only the subcritical ones will form. So, so we will have not only gravitational waves, but also the subcritical primordial black holes in the spectrum of black hole that are full. In possibility C, where phase transition happens, designates the end of inflation and settling from true vacuum to the false vacuum happens through that, we will neither have subcritical ones nor supercritical ones. And we notice that the peak frequency of such gravitational waves produced from such a first order phase transition will be shifted to 10 to power of 10 hertz peak frequency, which is quite large and is not able to be observed by LISA. So from also the bubble collisions, when we have first order phase transition, we will have the possibility of bubble collisions, which in this case turns out to be quite small, roughly of order 10 to power of minus 50. And so this scenario of bubble collision during first order phase transition will not give rise to substantial amount of primordial black holes. And I will conclude my talk here. So it's possible to construct an inflationary model compatible with latest Planck data and produces dark matter through as primordial black holes in the mass range of lunar mass, 10 to power of minus 17, sublunar mass, 10 to power of minus 17 to 10 to power of minus 13. The scale of inflation is quite small, so there will be no B mode, but there will be possibility of first order phase transition. And then depending on how the end of inflation happens and settling from false vacuum to the true vacuum can occur, we will have different signatures in the mass function for the primordial black holes and gravitational waves, from which we can examine the end of inflation. So thank you very much for your attendance and listening to my talk.
Thank you for the nice talk. So unfortunately, we are slightly behind the schedule. So if there is any question or comments, please, we will take one or two.
So there are two. Is that okay? These are the notifications for the time. Sorry.
It's okay. So is there any question or comments? So is there any correlation between the gravitation wave spectrum and the black hole mass distribution? Is there any?
So as I mentioned, the scale of inflation is ripe for producing a signature from first order phase transition that just falls into the LISA band.
I see.
And it also produces sublunar mass black holes. But it also depends on how fast this first order phase transition occurs. So it's not guaranteed that you can, depending on how fast the first order phase transition completes, and if it happens after the end of inflation via a slow roll violation, or it happens right, so inflation ends just exactly with first order phase transitions, the signatures will be different. And from these, the difference of the signatures, we can just distinguish different scenarios.
I see. Thank you. So let's move on to the next talk. Thank you very much.
Thank you very much. Goodbye.
So the next speaker is Yusuke Jinno, and the title is Deformation of the Gravitation Wave Spectrum by Density Perturbations. So please start.
Yeah. Thank you very much for giving this opportunity. Can you see my slide? Excuse me, can you see my slide?
Yeah, I can see.
Okay, okay. I will start. Yeah, I'm Ryusuji, not Desi. And today I will talk about deformation of the gravitational wave spectrum by density perturbations. And this talk is based on one paper with Valerie Donke and Enrique Rubira, both were at Desi. So let me start with the introduction. So now we all know that gravitational waves is a new probe to the universe. Gravitational waves are defined as the transverse traceless part of the metric, H either here. And if we expand the Einstein equation, we find that they will get the equation of motion sourced by the energy momentum tensor of the system. It's like the Lambert-Sum of Hij is Newtonian constant times some projection operator times the energy momentum tensor of the system. And detection by Lie-Van-Berg collaborations have been exciting us. And these two plots are summary for the operation 1, 2, and operation 3 from Lie-Van-Berg collaboration. So in today's talk, we do not focus on astrophysical Gaussian waves, but instead we focus on cosmological Gaussian waves. That is, Gaussian waves produced in a very early universe. And this slide tells you one of the advantages of using Gaussian waves as a probe to the early universe. Gaussian waves propagate without losing information because they have only surface coupling with our ordinary matter. But in contrast, for example, cosmic microwave background gets scattered above electron volt energy scale. So CMB tends to lose information if they're produced, if some event occurred, even if some event occurred in a very early universe. So this is one of the advantages of using Gaussian waves as a probe to the early universe. And from observational side, this is summary of ongoing and future experiments. The horizontal axis is Gaussian wave frequency, and the vertical axis is the dimensionless quantity, so-called omega. This is defined as Gaussian wave energy density, rho GW, normalized by the total energy density of the universe, and this is dimensionless quantity. And roughly speaking, there are three frequency ranges: pulsar timing arrays, space interferometers, ground interferometers. And if we are lucky enough, we have this kind of signal from a very early universe. So this is very motivating. This is introduction. So let me move on to the main idea of this talk. The central question we would like to ask is as follows. First, of course, Gaussian waves, after produced, they propagate in an inhomogeneous universe. This picture shows, this is illustration for the process. So after Gaussian wave production, these Gaussian waves propagate in a hot and cold spot in the universe. So our question is, what is the effect of this kind of inhomogeneity on the Gaussian wave isotropic spectrum? Here, isotropic means that directionally averaged spectrum. So yeah, this is just ordinary Gaussian wave spectrum. We want to study the effect of inhomogeneity on Gaussian wave ordinary spectrum, not anisotropy, because typically the angular scale for this inhomogeneity in the very early universe is much smaller than the detector can resolve. I mean, the detector is typically insensitive to this kind of very small scale inhomogeneity. So we consider effect on isotropic Gaussian wave spectrum. And one comment is that anisotropy of the Gaussian wave spectrum is now recently a very hot topic. So these people already started to study this effect. But in this talk, I will focus on isotropic spectrum. And the next slide shows kind of intuitive explanation of the effect we point out. So let's compare two cases. One is Friedman-Robertson-Walker case, and the other is realistic inhomogeneous case. If the universe is completely Friedman-Robertson-Walker, then after Gaussian wave production, the Gaussian waves propagate towards the observer, and the effect, the only net effect, is the redshift of the produced spectrum. So there's nothing interesting in this case. But in contrast, if the universe is inhomogeneous, then depending on the direction of the Gaussian waves, for example, in this example, this Gaussian wave propagated in a hot patch and then next cold patch like this. And this Gaussian wave propagated in cold patch and hot patch. And as a result, different directions receive different redshift. So as a result, if we see the gradation wave directional average gradation wave spectrum, we expect that gradation wave is somewhat smaller compared from the original spectrum. And this is the effect we want to study in this talk. And this slide shows a bit more detailed stuff about our final result. So let's take log frequency in the horizontal beam, in a horizontal direction. And suppose that we focus on one frequency beam at the sourcing time. And this is gradation waves source at the sourcing time. And what we eventually get is the deformation of this spectrum by by biased Gaussian, because gradation waves propagating in a hot patch tend to move this direction, and gradation waves propagating in a cold patch tend to move in this direction. So as a result, what we get is that gradation wave spectrum at the observer location is convolution of the gradation wave spectrum at the sourcing point times some biased Gaussian. And as I will explain later, this picture takes into account at least part of the relevant contributions. I will explain this later. So before moving on to the derivation of my result, our result, let me define the setup more clearly. We assume any gradation wave source in the very early universe. That is, we assume whatever source at the gradation wave production time slice. For example, we can have first order phase functions, or we can have gauge field production, or preheating, or topological effects like this. And on top of this, we expect that the curvature perturbation, these blue and red spots, exist simply from inflation. And these curvature perturbations enter the horizon later. And for these curvature perturbations, we assume single clock. That means gradation wave production occurs in the same way among all the patches, only up to time shift. This is our assumption, just for simplicity. And we assume that curvature perturbations are somewhat enhanced compared to the CMB value. So our study is related to T-gauge study, but we do not assume any T-gauge formation. We just study the effect on gradation wave propagation. And finally, we assume hierarchy in scales, two hierarchies. One is the hierarchy between the detector resolution and typical length of the curvature perturbation. This is one hierarchy. And another hierarchy is that the length of the curvature perturbation is much larger than the gradation wave wavelength. We assume these two hierarchies. So this is the main idea. And let me quickly derive our master formula. The hierarchy in scales I explained some seconds ago justifies using so-called geometric optics. Geometric optics means that infinitely short wave gradation wave rays propagate inside very long wavelength density perturbations. So it's like this. The hot and cold spots are density perturbations, and the gradation waves have infinitely short wave compared to this density perturbation. And if we give this kind of setup, we have several effects on these gravitational wave rays, just like CMB. So in the next slide, I will explain some CMB effects replacing these gravitational waves with photons. But what we eventually want to discuss is these effects on gravitational waves. So in the next slide, I will replace gravitational waves with photons. I will explain Sachs-Wolfe effect and the integrated Sachs-Wolfe effect. So the first one is Sachs-Wolfe effect in CMB context. It says that the temperature fluctuation is contributed from two terms. One is phi s, and the other is minus 2/3 of phi s. And here, phi is the perturbation which appears in this here in the conformal Newtonian gauge. And we can safely assume that phi equals to psi here. So both are essentially phi. And the level S means at the source position. And yeah, for example, let's take time axis or some direction in this horizontal axis. And let's take Newtonian potential phi in the vertical axis. And suppose that in this direction, we have positive Newtonian potential. And let's start from this high position. And the first term says that when photons climb down from the potential, they get some frequency gain, which is positive, 1 plus phi s. This is the first term. But on top of that, if the photons are in positive Newton potential, the temperature is slightly smaller than the average temperature. And if you calculate in a matter-dominated universe, it is minus 2/3 of the Newtonian potential. So this is the second term. This is the Duck's-Wolf effect. And integrated Duck's-Wolf effect is a bit different. If the Newtonian potential is time independent, then when the photons climb up and climb down the potential, then there's no net effect between the before the climbing up and after climbing down. But in reality, the potential, Newtonian potential is time dependent. There remains net effect on the photon frequency. This is integrated Duck's-Wolf effect in CMB context. And we expect similar effect on gravitational wave propagation. And the master formula we derive is this kind of form. We average the frequency and amplitude random walk over the infinitely many realization of the curvature perturbation, density perturbations. So this says that the gravitational wave spectrum at the observer point O is related to the gravitational wave spectrum at the sourcing point, but the frequency and amplitude is slightly modified depending on the curvature perturbations realized in the direction of the line of sight. So we use linear order result from geometric optics, which I explained previously, and both amplitude and frequency are contributed from Duck's-Wolf effect and integrated Duck's-Wolf effect. And once we assume this master formula, and also if we assume that the density perturbation is Gaussian, then this quantity is strictly calculable actually. And what we get is this kind of convolution with linearly biased Gaussian. Here K has this Gaussian term and also linear bias like this. So now let me show some numerical result. First, let's assume that the gravitational wave spectrum at the sourcing point is very spiky, this blue line. The horizontal axis is frequency, and the vertical axis is gravitational wave spectrum at the sourcing point or at the observer point. So let's assume spiky gravitational wave spectrum at the sourcing point. And if the integrated density perturbation is order 10 to minus 3 minus 2, then we have this kind of very large deformation effect on this frequency thing. These three red lines are for 10 to minus 1, 10 to minus 2, and 10 to minus 3 for the integrated density perturbation. And more realistically, we expect that the gravitational wave spectrum at the sourcing point is more smooth. So we took one example from gravitational wave spectrum from phase transitions, from bubble collisions. In this case, in a simplified model, the gravitational wave spectrum is frequency cubic in the low frequency tail and frequency inverse in the high frequency tail. And if we assume this spectrum at the sourcing point, then if the integrated density perturbation is ordered 0.01, we have this kind of deformation effect on the gravitational wave spectrum. So this is the main result, but actually our prescription had some subtleties, so I will explain this in the next two slides. First, for the smooth spectrum case, this case, the deformation of the Gaussian wave spectrum is somewhat smaller than this spiky case, and I'll explain the reason. For the spiky case, which means that if we focus on bin by bin, only leakage from the central bin occurs. So in this case, our prescription is safe. But for the smooth case, the second case, the leakage and inverse leakage from the neighboring bin almost cancel out. So the net effect we have in the end is some remaining term from after canceling out. So in this case, our calculation takes into account only part of the whole effect. And this slide explains the reason, but I think I'm running out of time, so I will skip this slide. And the second discussion is consistency with Gaussian wave anisotropy. If our Gaussian wave detector has enough directional resolution, then that detector can see the frequency shift and the amplitude shift of order curvature perturbation like this. But what we discussed in this talk is that even if our detector is insensitive to direction, we still expect some effect on the Gaussian wave isotropic spectrum, even though the net effect is somewhat suppressed compared to the Gaussian wave anisotropy. This is consistency with Gaussian wave anisotropy studies. So let me summarize. Gaussian waves propagate in an inhomogeneous universe, and the inhomogeneity deforms the original isotropic spectrum. And in our formalism, if the original Gaussian wave spectrum is spiky enough, then our formalism is safe. But if the spectrum is smooth, our result is just takes in account just part of the whole effect. So our result is just implicative. And also Gaussian wave anisotropy is important, of course. So the message from our result is that careful comparison between theoretical and observed Gaussian wave spectra, the blue and red lines in the final slides, may reveal the intermediate scale curvature perturbations. And in order to fully pin down this effect, we need second order perturbation theory. And this is what I'd like to work on in the future. Thank you very much.
Thank you. Thank you for the interesting talk. So is there any question or comment? So there is question from Yun Jiang. So Yusuke, can you read it for the participants?
Would this deformation have to be negligible for the sources which is at a late time? This deformation effect is actually first discussed in the context of astrophysical studies. I mean, I cited one paper, Laguna Rawson Schroeder Ines, 2010, and their main focus is Gaussian wave deformation in the present universe. So, yeah, this effect is not negligible, even in the present universe. I mean, for the astrophysical case, but typically the density perturbation realized in the present universe is not that large. So, I mean, we have larger playground, larger room for the deformation effect in the early universe compared to the present universe.
Thank you. So if there is no other question or comments, then let's thanks to the Yusuke. Thank you very much.
Thank you very much.
Next speaker is Carlos Tamaric. Are you ready? Are you there?
Yes, I'm ready.
Oh, yes. So please share your screen.
Wait a minute.
Yes. So you have 15 minutes for your talk and 5 minutes for the discussion.
Very good, thank you.
Yes. So the next speaker is Carlos Tamarit at Technique University Munich, and his talk title is "Gravitation Waves as a Big Bang Thermometer." So please start.
Okay, thank you for all the audience to listen to this talk, and thanks also for the organizers to accepting the abstract and giving me the opportunity of presenting this work, which was done in collaboration with Andreas Lingwald at TESI in Hamburg, Germany, and Jan Schütte-Engel, who was a PhD student of Andreas and is now at the University of Illinois, Urbana. So let me give a broad experimental context. So as we have seen, we are in the past years enjoying having access to a new window for observing the universe, namely the exploration of gravitational wave signatures. And many of the upcoming and current experiments are exploring regions in which gravitational waves with frequencies below 10 Hertz. And this covers a region above 0.1 Hertz, which is above the noise from Dwight force and mergers. And then this means that we can explore gravitational waves sourced by processes in the early universe. But as we can see in this plot, there's nothing usually quoted for higher frequencies. And the question is this interesting? So of course, it's interesting because high frequencies probe high energy processes in the early universe. And moreover, as gravitational waves interact weakly, they can travel undisturbed, so we can really probe the early universe with high-frequency gravitational waves. So what's the aim of the talk is to obtain state-of-the-art predictions for the spectrum of gravitational waves sourced by thermal fluctuations in the hot Big Bang plasma, and discuss current bounds and prospects for experimental detection. Why is our work interesting? We generalize theoretical predictions for the spectrum of thermal gravitational waves that were known for the standard model to arbitrary models. And we have studied experimental prospects to detect these high-frequency gravitational waves by using conversion of gravitational waves into electromagnetic waves in action experiments and in a proposal with a Gaussian beam. So the plan of the talk is to review the primordial gravitational spectrum from thermal fluctuations, and then I'll move briefly give predicted spectra for the standard model and for standard model extensions such as the standard model axion seesaw hidden scalar theory or the neutrino minimal standard model. And then I'll review current bounds and talk about future prospects. So how does the thermal plasma generate gravitational waves? So as we saw in the talk by Ryusuke, gravitational waves are sourced by fluctuations of the metric tensor, which satisfied whose transverse traceless part satisfies a wave equation, which is sourced by the transverse traceless part of the stress energy momentum tensor. So in order to generate source gravitational waves, we need a non-zero value of this transverse traceless part of the stress energy momentum tensor. So do we have this in the hot Big Bang plasma? And yes. And these anisotropies can be sourced by viscosity effects and large length scales, but also by plasma absorption emission effects of thermal excitations at small scales, as was pointed out by Leine and Guillier. So this means that we believe that the early universe was a hot thermal plasma, so there's a guaranteed background. Of course, it might be small, it might be very challenging or impossible to detect, but it's a guaranteed background, and it relies on very well-known physics that is less speculative than others. There's other sources of gravitational waves, such as inflationary heating or phase transitions, but this one, in principle, relies on very common physics. Now, of course, gravitational waves are Planck suppressed, and the rate of thermal emission will be small, but this emission accumulates since the Big Bang, so it can have time to accumulate to maybe a bigger than expected value. And the peak of emission happens at its time at around the temperature, but it's redshifting at approximately the same rate as the frequency of gravitational waves emitted in previous times. And this means that the power at the peak of emission adds up constructively. So we expect a peak in the microwave regime, and then we can call this the cosmic microwave gravitational background, or CGMB. And the big hope is that, I mean, if one could measure it, which is still it's very speculative, but one could perhaps measure the maximum temperature reached by the hot Big Bang. What do we need to compute this spectrum for thermal emission? We just need to fix the particle content of a theory with some particles in representations of the gauge group of your theory. So these representations are classified by the Dynkin indices of the particle representations, which are associated with the traces of the generators. So we need to know the Dynkin indices, we need to know the gauge and Yukawa couplings and the runnings, and we need to know three functions that count the effective numbers of relativistic degrees of freedom in plasma, which are these known G star rho, G star S, and G star C. So what are these G star functions? So they are related to parameterizations of the energy density, the entropy density, and the heat capacity of the thermal plasma. And they count the effective numbers of degrees of freedom. And the nice thing is that they can just compute it knowing the microscopic theory by standard thermal corrections to the effective potential. So one can obtain this effective number of relativistic degrees of freedom just by considering the thermal corrections to the effective potential and their derivatives. So if I have my theory with I fix my particle content, then I can fix my thermal correction to the potential and I can compute these quantities. So what is the rate of gravitational wave production? So it's related to correlators of the time derivative of the perturbation of the metric. And as pointed out by Giglieri and Leine, so the time derivative of the energy density in gravitational waves has a redshifting part as radiation, like here, and then it has a source term, which is given by a 2-point correlator of the transverse traces stress energy momentum tensor. Now we can just define it in terms of a dimensionless quantity, eta hat. And okay, then what are the results for this eta hat? So at small momentum, large length scales, there's a source from viscosity effects, and it's dominated by hypercharging interactions of right-handed leptons. And there's a known formula which relates it to the viscosity of the plasma and the thermal Debye masses of the gauge bosons in the plasma, which can be computed from the Dynkin indices that introduced before. What happens at short length scales or large momentum? And then this eta hat gets contributions from thermal excitations in the plasma. So Leine and Giglieri generally computed this at full leading order. And in the standard model, and we could generalize it to arbitrary theories. And we can express this as leading long contributions plus a sum over the gauge groups of some loop functions, which are here in pink, times some coefficients just determined by the Dynkin indices, and multiplied by the running couplings with the temperature of the gauge couplings and the Yukawa couplings. Okay, what are the state-of-the-art results? So on the left-hand side, we show the results coming from shear viscosity effects. And on the right-hand side is the high momentum due to the thermal excitations of the plasma. On gray is the leading order, and in color, the leading log, and in color is the full leading order. In between this region, we cannot trust the computations. And we see a slight dependence on the temperature. Let's focus on the contribution from the thermal excitations in the plasma. And here we have this eta function as a function of k over t. And with the dashed line, we show the results at leading log order. And in the color lines, we show the results at full leading order. Okay, now we have to integrate this spectrum, this rate of emission. And then for this, we need to account for the expansion of the universe. And then for this, we just need to use the relation between the temperature and time, which is obtained from entropy conservation and Friedmann's equations. And then we have just a dependence on these effective numbers of relativistic degrees of freedom that we introduced before. And we have to account between the relation of the co-moving momentum k and today's frequency by accounting from the redshifting of the scale factor. So when we do this, we get a formula for the relative energy density in gravitational waves per logarithmic frequency interval, which has some integral of this function eta hat. So this integral is dominated by the high T contribution, in which all G functions tends to a common limit. So we can get an approximate result which scales linearly with the maximum temperature reached by the hot big part. So there's a linear effect with the maximum temperature. So this is like a thermometer. So, and for future reference, we can introduce this dimensionless strain HC, which is related to the energy fraction omega by the following formula. So what are the main features is that the peak frequencies are in the gigahertz regime, so microwave regime. And these peak frequencies also depend on the effective number of relativistic degrees of freedom at the maximum, at the time of maximum temperature. And the amplitude at the peak also can be related to the standard model 1 by a rescaling factor, which depends on the ratios between the standard model effective degrees of freedom at high temperatures and our model. So this means that for models which have more degrees of freedom than the standard model, the peak emission will be smaller. So the standard model, in this sense, is the optimal, gives a higher power. What happens if the maximum temperature very, very speculatively goes above the Planck mass? So then we cannot ignore the back reaction of produced gravitons, which the previous formula ignored. And then one expects gravitons to reach thermal equilibrium and decouple at the Planck mass. And then the spectrum of gravitational waves is just an equilibrium distribution with a temperature redshifted from Planck mass to today. So the temperature of the blackbody spectrum of gravitational waves would be related to the temperature of the CMB by a rescaling factor given by the ratios of the effective relativistic degrees of freedom today and at early times. So the standard model results, as we can see, the spectrum scales linearly with the temperature, and it peaks in the gigahertz region, so far from the upcoming and space interferometer experiments. And we can also compute this for extensions of the standard model, particularly no extensions that have a well-defined history, cosmological history, and where we can predict the reheating temperature. So in this case, we can consider the SMASH extension of the standard model or the neutrino minimal standard model. And here we have included also the spectrum of gravitational waves emitted during inflation. And what we can see here is that the thermal spectrum is a well-defined component that is separated, has a separated peak from the spectrum coming from inflation. What are the current experimental bounds? So they come from direct searches, they're from interferometers, cavity experiments that measure the rotational depolarization, experiments measuring the spin precession, or the Gertzenstein effect, which is the partial conversion of gravitational waves into electromagnetic radiation. In particular, one can recycle action experiments which look for photon action conversion to, we can, use their bounds and translate it to gravitational waves to photon conversion. So there's also indirect searches because this Gertzenstein effect can modify the CMB spectrum, as was pointed out by Domke and Sid. So let me give a picture here. In the vertical axis, the dimensionless strain, and the horizontal axis, the frequency. And here are the space-time interferometers, and these are some laser interferometers and on Earth, and also action experiments like ALPS, OSCAR, and CAST, and then some haloscopes, and these green lines are the indirect bounds from the CMB. And we see that, okay, here this curve is the cosmic gravitational microwave background from gravitational waves that reach equilibrium at Planckian temperatures. And this is the maximum spectrum that we would have, and it's still 10 orders of magnitude of the current bounds. What are the future prospects in the laboratory? So let's think about this gravitational waves, electromagnetic wave conversion in vacuum, then known as the Gertzenstein effect, as I said before. And this relies on the conversion of gravitational waves that are orthogonal to some magnetic field into electromagnetic radiation. So, and this extra electromagnetic radiation is second order in perturbations of the metric. So it's weak conversion, and the emitted power which is proportional to this dimensional strain I introduced before, and scales with the B field and the length and the area in this manner. And for this addition to be, to work, we have to have photons that add up coherently, which implies that the frequency must be above some cutoff. Then we can compare the numbers of some axion experiments, which have these strong magnetic fields, and the figure of merit of the sensitivity is this BLA to the 1/2. And this is the cutoff frequency. And this is the reach in the dimensional strain from heterodyne sensors or single photon sensors. And we see that the best is around dimensional strain around 10 to the minus 22. But we saw that the maximum strain reached, for example, thermal gravitational waves in equilibrium is 10 to the minus 32. So we're 10 orders of magnitude away nowadays. What happens if we use a Gaussian beam? So this is a proposal by Lee and collaborators, in which by putting a Gaussian beam additional to the magnetic field, then one can get photons generated in the orthogonal direction at first order in the metric perturbations. So in order to detect them, one has to shield, remove the photons emitted by the Gaussian beam. So one can put a reflector and try to see one detects these first order photons. And we gain a lot by the fact that these photons are first order, but of course we lose by the high noise due to the strong fields. And then there's some figure of merit for the reach in the sensitivity on the dimensional strain, being like this. And the best what we can estimate is a reach which would be, instead of 10 orders of magnitude away from the equilibrated cosmic microwave, gravitational microwave background, only a factor of 1,000. And there's a possibility to improve current technologies by a factor of 1,000 by improvements in the power of the gyrotrons, stability of the running time, and the count rate. And in this manner, one could, so the current bounds from axion experiments, as I said, 10 orders of magnitude away. But with this Gaussian beam, we could be 3 orders of magnitude away, but potential improvements could probe the equilibrated cosmic gravitational microwave background. Still, for realistic extensions of standard model, we would still be away. So this brings me to my conclusions, which is that there's a guaranteed background of gravitational waves from thermal origin. It peaks in the microwave region, and we call this the cosmic gravitational wave background. The peak value and frequency are directly related to the maximum temperature of the Big Bang and the number of relativistic degrees of freedom at early time. So if we were able to measure this, we could perhaps estimate the maximum temperature reached by the hot Big Bang plasma and the numbers of degrees of freedom at early time. So the current bounds are many orders of magnitude above the maximum possible cosmic gravitational wave background. And we have a proposal to use the Gertrude effect with a Gaussian beam that exploiting improvements in current technologies could lead to reaching this equilibrated cosmic gravitational wave background. And I'll finish here, and thank you for your attention.
Thank you very much for the interesting talk. So is there any question or comment? So the CCMB gives the information of the weighting, right?
Yeah, exactly. So that will be the hope.
So is it insensitive to the information of how fast the weighting occurs?
Well, there could be, of course, if reheating is not instantaneous. For the integration over time, we assumed directly radiation domination all the way. So there could be a period of transition, for example, during reheating. There could be a brief period of matter domination. As long as this period is comparatively small to the rest of the period after inflation, this estimate will be valid.
I see. I see. Thank you.
Thank you.
So is there any other question or comment? If not, thanks to the Carlos. Thank you very much.
Thank you.
Thank you. So the last speaker is Alexandro Lenosi. So are you there?
Yes.
So,
do you hear me?
Yes. So please share your screen.
Does it work?
Yes, I can see it. Good. So the last speaker is Alexandro from Francisco Teji, right? You're from Teji. Okay. So we will talk about low mass bounds on peak dark matter. So please start.
Thanks for the introduction, and good morning or afternoon to everyone. And also thanks for the possibility to talk at PASCOS. I'm going to present a recent work of mine completed during my first months of PhD at DESY, collaboration with my master thesis supervisor, Francesco Deramo from Padua University. And in this work, we developed a methodology to find lower bounds on the mass of dark matter produced by a freezine in a model-independent fashion. So let me introduce my topic. So as proven by observation from galactic to cosmological scales, dark matter makes up 25% slice of the cosmic budget pie, but its nature is still unknown. In particular, we consider a paradigm to describe the dark matter production, known as freezine, and we will try to put constraint on this scenario using observation of ordinary matter. In particular, this 5% slice is mainly made of intergalactic gas, and this cool component of intergalactic gas is a filamentary structure called Lyman alpha forest. That is one of the main observable used to constrain the dark matter mass. Indeed, in 2017, Ville et al. Found limits to thermally produced dark matter mass, known as warm dark matter. And depending on the assumption on the data set and the methodology to model this Lyman alpha forest, they found a stringent bound of 5.3 keV and a conservative bound of 3.5 keV. And we want to use these results as a starting point to constrain also non-thermal model of dark matter. So let me specify our framework. We consider an homogeneous and isotropic Feynman-Robertson-Walker universe, and the evolution of the relativistic degrees of freedom is described by the standard model of particle physics. Then we consider dark matter particles produced by a freezine. And this term freezine refers to particles which are so weakly coupled to the thermal bath that they do not attain a thermal equilibrium. So the number density is built up coherently until the rate of interaction between the plasma and the dark matter particles drops below the Hubble rate. And this process is dominated at low energy, so it's called IR dominated, and we call this energy M. So our feebly interacting massive particle chi with mass m chi and g chi degrees of freedom will be characterized by a non-thermal phase-space distribution. We assume a Maxwell-Boltzmann statistics, not distribution, for the dark matter particles, and this is an excellent approximation, as one can verify a posteriori. And finally, in this work, we consider dark matter production happening during the radiation-dominated era, where we know the dependence on the Hubble parameter on the temperature. So to characterize the properties of our FIM dark matter candidate, we have to know its phase-space distribution. That's called PSD F chi. And this is found by solving the Boltzmann equation, which is written like in the blue box. In the right-hand side, the collision operator describes the interaction between the dark matter particles and other particle species. And in particular, we consider these specific topologies where we have n particles of dark matter produced via scattering or encounter of L bath particles, and also other M bath particles are produced. When one wants to solve this equation, considers dimensionless variables, and the time dependence is traded for temperature dependence, and then we introduce this variable x, and at large values of x, usually the rates drops down the Albor rate, and then the collision term becomes irrelevant. So the phase-space distribution basically only redshifts because of momentum redshift. So we get rid of this time dependence, considering this comoving momentum Q, which also carries a definition of the phase temperature in analogous way at what happens with, for example, neutrinos. And the solution of the Boltzmann equation is then obtained straightforwardly, and the collision operator in this case becomes only a function of temperature and momentum, does not depend on the f-chi phase-space distribution, and is the integral over the Lorentz invariant phase space and the product of the initial phase-space distribution. And also there is the amplitude, which we consider as a constant, since freezing is IR dominated, and this is an excellent approximation for IR dominated freezing. So we focus on some specific topologies. That is, we have two-body decays, three-body decays, and scattering, and we consider a single or multiple production. For each topology, we choose a benchmark that is a relation between the dark matter, the mass of the bath particles involved. In this way, we can have only one mass dependence. So we have a dependence on the dominant mass scale and on the mass dark matter particle mass. On the right column, we have an analytical estimate in the case of two-body decay, three-body decays, and scattering. And notice that the multiple production, of course, only contributes with a normalization factor. Here, we show that PSDs for the three single production topologies, so two-body decays, three-body decays, and scatterings, and we choose the relevant mass K to be 1 TeV and the dark matter mass to be 30 keV. And we compare the numerical solution, which is in solid black, with the analytical estimate in red, and the Maxwell-Boltzmann distribution in blue dotted. So we see that the PSD is indeed very non-thermal, and the distribution can be fit with this very simple form, which is very which is suitable for dark matter produced by a single process. And from this, one can find analytically the first two moments of the PSD. This is the average comoving momentum, and a quantity which is the second momentum and is often referred as warmness. But how do we put bounds on dark matter mass? In literature, there are many ways to do that. First is usually done by requiring that free streaming length scale, that is the average comoving distance traveled by the dark matter mass from the time of production to time of equality, is less than the free streaming length of some world dark matter reference model. And so we require that structure formation is suppressed only on very small scales. And the PSD dependence enters in this average velocity. Instead, as shown in article by Kamada and Yanagi of 2 years ago, a good way to impose a warmness constraint is to use this quantity, and we can obtain a simple analytical estimate of the dark matter bound depending on the second moment of the distribution, so the warmness. However, the most reliable and also severe, but still simple constraint comes from the computation of the matter power spectrum, linear matter power spectrum, computed usually with Boltzmann code, and we used class, for example. So one can define a transfer function that parameterizes the power loss with respect to a standard CDM model. And we can define this in 3 dimensions or in 1 dimension with a projection and have this bound I will explain in the next slide. And then another independent constraint on using the power spectrum is a number of Milky Way satellites that must be greater than the number of satellites we observe. So let me tell how we constrain the mass using a relative transfer function. We see that to extract bounds from transfer function, we can define an half mode, which is a cutoff in the power spectrum. And this is a mode at which the transfer function drops by a factor of 2. So we require that the cutoff happens at scale smaller than the allowed by the Lyman alpha bound from working matter. And another better motivated criterion is based on the fact that the observable of Lyman alpha is a flux over a line of sight, so it's a 1-dimensional observable. And so one can define this fractional area delta A that represents a percentual suppression of 1D power in the scale probed by the Lyman alpha survey, so between Kmax and Kmin. The max IRS XQ100 surveys explore the range between 0.5 and 20 megaparsec to the -1. And this is the violet region in these cartoon plots. So we impose the power suppression to be less than in the allowed wonder matter models. And transfer function in this plot will be allowed as one has no suppression. And transfer function in this right plot will be forbidden. Now we can apply the criterion to benchmarks to extract the bounds on parameter space. For 10 reasons, I will show you only the results for 2-body decays. And the parameter space is made of the decaying particle mass, M1, the dark matter particle mass, M chi, and the fraction of dark matter abundance with respect to the total dark matter reproduced by Fresene, and the mass of the other particle produced by decay, which makes this phase space suppression of R2. And we have this, we have the plots fixing F to 1 and R2 equal to 0. And for conservative and stringent bound, we have constraints in the M chi M plane. We compare different criteria used in the literature, and we obtain conservative bounds comparing a FIMP model with the wonder matter model with this wonder matter mass. In general, the most severe bounds are imposed by the criteria obtained by the transfer function, and they overlap over almost all parameter space, but also the warmness criterion works quite well, so it's confirmed. And notice that the bounds on dark matter mass are more severe if the decaying particle is lighter. Of course, this is because the film production happens later and the number of relativistic degrees of freedom drops down. You see the substantial change around the QCD phase transition. Since the delta A criterion is the most best motivated one, also the most stringent one, we exploit it in the further analysis. So we can ease the bound on the film dark matter, allowing some phase space suppression. So we consider R2 different than 0 and relevant. And we put constraint on the M1 R2 plane, plotting isocontours of the minimum dark matter mass. So we have conservative and stringent bounds. And notice that for more degenerative mass spectra, that is R2 very large, so here hub. The bounds are below 10 keV for TV M1 and below 20 keV for MEV decaying particle. Another way to ease the bounds is to consider FIMS as a subdominant component of dark matter. So considering a FIM plus cold dark matter mixed model. We compare the three criteria that use dark matter linear power spectrum, and we see that mass bounds are still above the KV for fractional FIM dark matter component as low as 0.3, 0.2, and they go away for fractional component even smaller. So let me conclude with some further developments which can be explored in the future. The obtained bounds hold as long as FIMs are produced during thermal bath or radiation dominated era. So we have no strong proof, since we have no strong proof that this is the case for temperatures higher than the MEV where Big Bang nucleosynthesis happened. It's interesting to see how the bounds on FIM dark matter change if we consider a different cosmological background. So motivated scenarios are an early matter domination era, for example, during a non-adiabatic evolution of inflationary reheating, or a more exotic case in which some new species with an exotic redshifting density is there and dominates the universe. In this case, the universe can expand faster, and we can imagine that FIMs can be lighter in this scenario, being more diluted. Another path we can follow is to apply this methodology to specific microscopic realizations, so portal models, dark photon, Higgs portal, and also to consider maybe UV-dependent freezing. In this case, we shall really update the formalism, since we consider the amplitude of our process to be constant due to IR-dominated freezing. Ultimately, the goal of our work will be to obtain constraints on FIM parameters given a generic FIM model using our methodology plus class. Thanks for listening, and if you have questions, I will be glad to answer them.
Thank you very much. So I think there is a question in the chatting window. So Alexander, can you read the question and then you can...
Yeah, let me see. I don't see the chat. I have to share, sorry. Can you comment why does lambda F free streaming lead to weaker bounds for FIMs, while warmness gives stronger bounds in agreement with the bounds using class? So let me share back. Let me share back. Sorry. So here, the free streaming length, if one goes in computing this quantity in an accurate way, will be dependent on the average co-moving momentum. One can see that this integral gets split in two parts. One is linearly dependent on temperature and on mass, sorry, and the other one is only logarithmic dependent. So this free streaming length will account only for average momentum. And you see here in the plots that the co-moving momentum is, yeah, it matters, but the quantity that changes the most for a non-thermal distribution is the sigma quantity. So the sigma quantity is very relevant for the dispersion of momentum, and the momentum dispersion is what determines the warmness of your FIM candidate. So yeah, usually one uses this free streaming length, and this is fine for thermal candidates, but for non-thermal candidates, momentum dispersion can be very different for thermal candidates, and so we have to account for that. I see another question.
Yes, there is another question.
If FEMS suppress the power spectrum at small scales like Warner matter, while no additional effect in the nonlinear evolution process, yeah, of course, there would be some nonlinear effects, but here we just focus on linear matter power spectrum and on the small scale suppression. So the methodology is to use the warm matter as a map to so that one can use simply the constraints found from warm matter and constrain a whole bunch of models for freezing produced dark matter. Since freezing dark matter has many parameters that can be free, this is a way to first put some constraint on the mass. Then one can account also for nonlinearities. But I mean, this will be similar to warm matter. There is always this mapping due to the fact that you have some momentum dispersion. It's another question.
He's on.
I have a possibly technical question. There may be multiple choices for the parameter to constrain warmness. Why does the satellite count provides weaker bounds than the other methods? I think this is due to the fact that if you see here, yeah, the satellites count is based on the power spectrum. So one may implicitly think that you will get a curve overlapping with the, for example, the red constraint here or the yellow and also the green. But this is not the case because of the number of observed satellites. So this is independent from the on the other constraints, and the number of satellites which is estimated is 60. But of course, this is a very uncertain thing since you have a bunch of astronomical uncertainties there. The satellites which have been observed are, I think, 15 or order 10. And then you account for the small coverage of your survey. So you multiply by a factor and you estimate that the distribution of the satellites is isotropic. So if the bounds is 50, these curves will move sensibly here. And yeah, this is only based on the literature, which says that there are 60 satellites there, but this is very uncertain. These plots is basically a way to see all the literature, how the literature can put bounds on the mass, and to see which is the most stringent one. Can one sensibly use bound from warmness quantity W for mixed warm and colder matter? I think no. That is because when you have a warm and colder matter mixed scenarios or thin plus cold, you should rely on some Boltzmann solver. So it's difficult to, I mean, you can consider analytically the case where all the dark matter is made of films or all the dark matter is cold. But when you have 50-50%, then you have to give up and use a Boltzmann solver. So the Boltzmann solver can only give information about the power spectrum, the linear matter power spectrum, and there you have these K1/2 cutoff and delta A suppression criteria, and you don't have, unfortunately, this water matter. That is why I didn't show here the green line. Have I answered?
Yeah, good.
Questions?
Is there any other question or comments? So if not, let's thanks to the Alexandro. Thank you very much. So
Thank
this
you.
is the end of the session, and we will have a break for 20 minutes. All right, 20 minutes. So thank you so much. So